In this video, I'm going to show you how you can calculate power for an equally replicated, completely randomized design using PROC power. So the code I've given you here is for specifically 3 treatments, and when that capital delta value is 1. So we want to be able to detect a difference between treatment means of magnitude 1. So what I have at the beginning of this code, this is called a comment for a code. So if I were to run this code, this part right here that's in green wouldn't actually run, but it's good for me to just kind of leave notes for what the code does. So I'll try to do that kind of throughout this code, so you know exactly what to put in. So the first thing here that I've said, title, power for delta equals 1, alpha equals 0.05. This is just something that's useful. It'll pop up at the top of all of our output so we know what our output is for. So if you change these values here, it might be nice for you to change what's up here so you can keep track of what your output is for. But the code will still run even if this title is incorrect. So just be a little careful about that if you don't update your title. So PROC power is a procedure that actually doesn't require any data set. It actually kind of just creates fictitious data and figures out what the power would be in that case. So for a completely randomized design, we could just think of that as being a one-way analysis of variance where our different groups are our different treatments. So to tell PROC power that we want to do analysis for a one-way ANOVA, we just write PROC power and then we type one-way ANOVA. And then we want to tell it what test we want to do. And so we're looking at the overall ANOVA test, so we say test equals overall. You can do PROC power for a specific contrast, but we're going to look at just in this video how you can do it for the overall test. So the first thing that we need to do for PROC power is we need to tell it to enforce that delta requirement that we want. And if we want to follow that conservative approach that we showed in class, we need to figure out how to get PROC power to do that. So the way PROC power works is you tell it what the different means are between the groups. And by doing that, you're also telling SAS how many treatments or how many groups you have. So if I have 3 treatments, then when I say group means equals, I need to have 3 numbers here separated by kind of this vertical line right here, which is right above your return key on your keyboard. So I could put in kind of any numbers I want, but to kind of help operationalize this, the easiest thing to do is for whatever delta value that you want, divide that value by 2, and then set one of the means equal to the negative of that value, and another of those means equal to the positive of that value. And then you set everything else to 0 so that they're all lying exactly in between, which is exactly the approach that we were going to take. So when I divide 1 by 2, I get 0.5. So I set, in this case, the first one to minus 0.5, the last one to 0.5, and I would set all of them equal to 0. So if I had, for example, 5 treatments and I wanted a delta of 1, then I would just need to add more zeros in this case. So there I have 3 zeros in the middle, and then I have a minus 0.5 right there and a 0.5 on there. But I'm just going to do this example continuing with 3 treatments. Then you tell it what your standard deviation is, and I'm going to say that's a 1. Now be careful, this is the standard deviation, so it's just sigma, not sigma squared, while in class we talked about defining sigma squared. So just be careful about that. This is the alpha value that I would use for my test. And n total, this is another thing you need to be careful about. This is actually asking you to define not what the r is, but what r times t is. So we've already told SAS what our number of treatments are by saying how many group means we have. So if I want to define an R, I have to do it by defining an N. So all I would need to do is figure out how many treatments I have, and then if I wanted that many replicates, I just multiply those 2 numbers together to get N. So when I define 6 here, that means that my replicate is actually 2, because 3 times 2 is 6. So that's just a little bit of side math that you'll have to do, but just remember that this assumes equally replicated treatments in this case. So this is what n total is. This is me defining how many replicates I have. SAS is also going to ask you to define power, but really you only need to define either end total or power. So in this case, we want SAS to calculate power for us given this number of replicates, or total experimental units, I should say. And so I say power equals, but I just put a dot right here. So it knows that it needs to calculate power given end total. This last option, plot, I'll talk about that in just a second. So we're going to comment this line out by just putting a star in front of it, rather than putting a /*. You can do that in some cases as long as this ends with a semicolon. But I usually stick with this type of commenting. So if you want to do a plot, you just need to delete that star. So if I run this code right here, it gives me some output. In my results window, it tells me everything that I put into it, and it says my computed power is 0.083. So not that great, but also not that surprising given what I put into it. I'm saying that I want to detect a difference of 1, which is exactly equal to my standard deviation. So it's hard to separate out the signal and the noise in that case. So if I wanted to maybe increase my total number of observations, let's say this is now going to be 18. So what that means is when I divide this by 3, that's 6. So I'm going to have 6 replicates per treatment. Let me highlight this again and then run it again. And so now my power is 0.270. So I could continue to do this until I get it to work, but one thing that's nice about SAS is that it can actually do a bunch of these end totals for me and make a nice sort of plot that I would like. So I'm going to change this back to 6. Now I'm going to remove this star so it actually will do a plot. So what this is doing is saying I want to create a plot of power where my x-axis is n, in this case my total sample size, and I want to calculate power going from 6 to 27. So this would be 2 replicates and this would be 9 replicates. When I divide 27 by 3, I get 9. So let me highlight this and click run. And we see this nice kind of smooth increasing trend. Again, it's because my delta is very, very small relative to my standard deviation. If I wanted to make delta a little bit bigger, I'm not going to change this code. Let's say we wanted to make delta 2. So I would just need to change this 0.5 to 1 and this to 1, because the difference between these two is 2. Now let me highlight this code again and select run. And here we see that our curve is increases a lot faster, and it approaches 1 once we get to about that 27 total sample size. I can also create this plot for multiple values of standard deviation. So here I just have 1 value entered. If I do a list of multiple values after standard deviation, it'll actually overlay a bunch of lines together. So let's say I do a standard deviation of 0.5, 1, 1.5. So here are 3 numbers, and it's going to create a plot for each one of these, just like I had before. So let me highlight this and press run one more time. So now I have 3 different lines. There's a legend here saying which is for which. So when my standard deviation is 0.5, I get high power very quickly. This is because there's less variation, and so it's easy for me to detect that difference. In this case, I've left it at a difference of 2, but I can change it back to 0.5. Sorry about that. Let's go back to the original example and run this again. Here we go. So again, this is for a delta of 1, alpha 0.05. So when my standard deviation is 0.5, I get higher power very quickly as I increase my sample size. The increase is much slower for when I have a 1 and a 1.5 standard deviation. So this would be 1.5 down here, and this would be 1. So you can kind of see what I was saying in class about how you might want to plot this for a variety of possible standard deviations or possible sigma values, just to get an idea of what a reasonable sample size might be that you want to use. Another thing that's nice about PROC power is, let's say I have a desired power. Let me make all this back to what it was. So I have a power that I want, but I don't know what sample size to use. So SAS can actually back calculate that for us, which we didn't see in class. So I'm going to change n total to a period. Let's say I want a power of 0.8. So I'm going to comment out this line. And so let me highlight this, click run. And so what this tells me is if I want a power of 0.8 and I want to have everything equally replicated, then I need to have a total sample size of 63. So if I divide that by 2, I get that I need 21 replicates for each treatment. And so the actual power I would be getting is 0.815. So that's one nice thing, that you don't have to actually figure it out for a range of values. But I also kind of like the plot to see how quickly we approach a certain desired power level. As far as calculating this on your own, you can do this actually inside a data step. So this is one way that we can get SAS to process our own sort of data. It is kind of difficult to do it. Normally this would create a data set in your work library in here, but by writing data null, I'm telling SAS to not actually create a data set. I wanted to do some computation but not create any data set. So here are just some parameters, very identical to what we had before, but using sort of the formulas that we saw in class. So T, this is going to be your number of treatments. So you just need to put in the number you want. This capital D is the delta difference of interest. So it was 1 up at top, and we'll make it 1 again. Sigma, this is the standard deviation you expect. Alpha, this I think most people know what that alpha means. R, this is the number of replicates per treatment. So this is easier to calculate than using PROC power, where you had to kind of do some math in your head to figure out what you needed. So this lowercase d, that's the non-centrality parameter. So you don't need to type anything in here. This calculates everything based off of what you have up here. And so this calculates the non-centrality parameter. This F null, this is calculating that threshold value to figure out whether to accept or to reject. And so this is done using the quantile function. So this is my F value. This is my upper value. So if my alpha is 0.05, then I want to find the 0.95 threshold. This is my numerator degrees of freedom. This is my denominator degrees of freedom. And then to calculate power, I use 1 minus the CDF function, where the value I want to evaluate the CDF at is my null value, which I calculated up here, on a non-central F distribution with this numerator, this many denominator, and this non-centrality parameter right there. And so this is just going to actually print something in the log of what the actual power is. So if you'll remember, the first thing I calculated for power was all these settings where n total was 6, so 2 replicates, and our power was 0.083. So let me highlight this and click run. So nothing pops up, but if I go to my log, it prints my power right here. So 0.083. And so that's how you can generate power values yourself using the data step. But for the most case, you probably want to use PROC power. This is just a way of verifying that the calculations we got in PROC power were actually correct.